Hello, sir. Shall we start?
Please, yes, sir.
Okay. Thank you. Good evening, all of you, once again. So, in the last session, I think we were discussing something related to the number theory functions, and I think a few more things on number theory related functions are left. And I wanted to actually discuss one problem also, which is prime number race. I have already introduced a little bit of things about that prime number race in the last session itself. I'll try to explain it more. And that particular problem actually tells you that how useful the computation software is, and at the same time it tells you that how mentally powerful the all mathematicians were. That also I would like to explain using this problem. Okay, so let me start sharing my screen first, and after that, if time permits, we will be going into some basic complex analysis, which is the topic of tomorrow's session. Actually, we will try to jump into that so that we will get more time for doing some extra problems towards the end of this workshop. Okay, let me start sharing my screen, the Sage window. Okay, the very last thing that we discussed is probably about finding powers modulo some particular number, and we were discussing something related to modular arithmetic congruence, etc., etc. And we have seen also that how to define polynomial ring over an arbitrary polynomial ring over an arbitrary ring, because usually we define polynomial rings over either the set of all rationals or the set of all real numbers or the set of all complex numbers, etc. But okay, even that I have not completely explained, but you might have already seen that if you have listened to last day's session, we have seen one general command using which we can define polynomial ring over any ring. Okay, that we have already seen, and we will be trying to discuss that thing much more. So the last thing we did is taking the power of a number modulo some other number. That's a very important problem in number theory. Not only in number theory, probably in abstract algebra also, when we are trying to construct several examples. That's actually a very good example, very good place where we use all these things. Now, to begin with, I will try to go into something called the Chinese remainder theorem, which all of you are familiar with. Chinese remainder theorem essentially says that if we have a system of linear congruence equations like x is equal to a1 mod m1, x is equal to a2 mod m2, x is equal to a3 mod m3. So three linear congruence equations are there, suppose, and suppose that we want to solve all these simultaneously, in the sense that find an x in such a way that x satisfies. See, x is going to be, since there are different moduli, possibly different moduli, what type of x we are looking for is x is actually an integer, but x must satisfy all these congruence equations. Therefore, if you substitute x to the first equation, it must be modulo m1, it must be a1. So let me just type. I think that's better, so that we can easily, so we will not lose focus on these things. So this is what the Chinese remainder theorem, or in short CRT, says. The system of linear congruences. X, I am using equal to because I cannot type equivalent to here. X equal to a1 mod m1 and x equal to a2 mod m2, etc. There are finitely many equations. X equal to an mod mn. So CRT says that if these moduli mi are relatively prime, then there is a solution. And CRT also gives that how to find the general solution. The solution is actually found out as a number, and CRT further says that x is going to be unique modulo m1 into m2 into etc. mn. Okay, so the solution is not necessarily going to be unique because it's a more congruence equation, and therefore we can find several solutions. For example, suppose that we are taking 5 modulo 5 x congruent to 2 modulo 5, then you will be getting 5 plus 2 is equal to 7 is a solution, 12 is a solution. There are infinitely many solutions once you have a solution. Therefore, you cannot expect a unique solution in the case of congruence equations, but what you can expect is it's going to be unique with respect to some modulo. Probably that you will be able to say. CRT says that there is a unique solution modulo the product M1 into M2 into etc. Mn. That's what a CRT, Chinese Remainder theorem, says is. Now, how do we find a solution using SageMath? Is that what we are trying to see? That x congruent to A1 mod M1, x congruent to A2 mod M2, etc. x congruent to AN mod Mn. So the very first thing we can probably try is, we have already seen how to define what you call congruent numbers or numbers in the ring of integers. We have already seen how to define. Can we make use of that? That's the very first thought that should occur to us. Can we make use of, can we define one particular ring and can we find out one solution in that particular ring? But in that case, the problem is that if you try to do that, the CRT, see that particular x, whatever you are finding as a solution to x congruent to A1 mod M1, that x will be an element of that congruence ring mod M1. Okay, that's actually the problem. So we are not getting, that particular x is not going to be an element in congruence mod M2. Okay. So if you try to do that, that's actually going to be a problem. Okay, we can at least try to see if that's that actually works or not. At least for one equation, one linear congruent equation, that works or not. So initially, let us try to see if this works. Try with x congruent to A1 mod just M1. Let us just try to see if Sage is at least capable of doing this or not. Okay, so how do we solve this? So remember that the CRT is not dealing with a system of linear congruences in one particular integer mode ring. Okay, that we have to remember. Okay, so the next step probably we will, okay, I will just try to do that first, do this first, and after that we will see. So the first equation we can probably consider is x congruent to x equal to, I am writing, so 2 mod 5. So this is one equation. So how do we try to solve this? That's the first thing that we are going to see. Okay, anyway, let me just share the Google document where I will be copying and pasting all these things. I have already copied and pasted this thing to, okay, let me just once again take that, copied. Now the link is here. Okay, to solve that, the very first thing we have to see is, can we define a polynomial over this particular M1? So M1 we have taken to be here. Here our M1 is nothing but 5. Okay, let us define a polynomial ring over Z5. Polynomial, this is how we do this. So we are going to define by, we are going to define a polynomial ring, a univariate polynomial ring, which means that there is only one variable. So polynomial ring over say, so we have not defined Z10, but maybe we can do it here itself straight away without integers 5. So suppose we take M1 to be equal to 5 to make it general. So M1. Now we are defining the polynomial ring over, okay, maybe we can even define Z M1 equal to, okay, we will do this, and then, okay, this does not make much sense. Okay, we can define directly M1 itself, directly 5 itself without using this notation M1. So Z5, this is what we are defining. Now what do we want to solve? X congruent to 2 mod 5 is what we want to solve. So where this 2 is, let us see. Is this 2 actually there? List the elements in Z5 to see if 2 is actually there or not. So 0, 1, 2, 3, 4. 2 is there as the second element. Second in the sense that the counting starts at 0. Therefore, second element is actually the third entry. Second element in this list. So, or the third entry we label as the tooth element. Z5 2. Okay. Now let us call this A2. Let us name this A2 as. So instead of using complex notations again and again, Z5. This is 2. And let's see what this A2 is, just to make sure that we are doing it right. A2, we require this. A2 is 2. Remember that this is not actually a list. Z5 is not a list. Here we converted that into a list. If we convert this into a list, then only we can use Z5 in square bracket 2. Otherwise, we need to use the function like notation. There are two types of argument type notations in SageMath. One is function type. In function type notation, we use ordinary parenthesis. In the other one, for accessing elements in a list or tuple by using the index. Index means the number 0, 1, 2, 3, etc. For using elements in the tuple or list using the index, we use the notation square bracket. But here Z5 is not considered to be actually a list, but it is just an integer ring type object. So for accessing, ordinary bracket needs to be used. What is the wisdom behind all these things? If you ask me, I don't exactly know, because as I told previously that SageMath, several concepts were created by different people. So some people might have thought that okay, we can keep this as the notation there, or otherwise it's also possible that there is an intelligent reason for keeping the ordinary bracket instead of square bracket. I don't exactly know what the reason is. What I believe is this is the reason, that many different mathematicians, computer scientists might have created different modules in SageMath, and there was no strict standardization possible at the time of defining all these things. Maybe after some time they might have started standardizing certain things, giving some extra guidelines, do this, do like that, so that the notation will be standard throughout. But for many of the things, you can observe that the notation is not standard. For similar things, you can see different notations. Similar looking like things, you can see different notations. So A2 is here. Now just use the solve command. Try to use the solve command. Solve and see if it's working or not. Solve. So what we are supposed to solve? We are supposed to solve the polynomial equation x minus 2. Okay, because x is already a variable over Z5, x minus 2 should give a x minus 2 or A2. X minus 2, I don't know whether it will make some sense. We can try to see x minus A2. X minus A2 and solve this. Maybe I don't know whether square bracket is required. Let us try. Solve for this, and what the result is? There is no result. X is not a valid variable, or x is just a polynomial variable supposed to be. X here it is not solving for this. Okay, maybe we can do one thing. So let us try to define, instead of that, or A2 is already an element in Z5. Let us try to remove that x meaning by redefining x to be a variable and see. Unsupported operand parents for symbolic ring and ring of integers modulo 5. That means that this is not actually supported in SageMath. Okay. Just 1 second. So this is not essentially supported, it seems. Just one second, I'm just trying. Okay, so instead of that, what you can actually try to do is, so instead of that, this solve is a command that is actually meant for this normal rings. Normal ring in the sense that normal, not finite fields, but the fields and subfields of complex numbers. Okay, let us try to do something else. Let us see another command. Okay, this we can see that this is not actually working anywhere here. Let me just copy and paste first of all. We have already tried these things. We have tried two things. What is the first thing? We tried with this and we tried without this. Both these things are generating error. So I am updating the Google document now. So updated, which actually gives an error. Now let us try to do something else. I have already copied and pasted. So now this definition I am removing. Now instead of using the solve command, let me just try to do something else. I am going to use something called solve modulo. Okay, an alternate or a different what do you call an analogous version to solve in integer modulo some other number or finite ring is solve modulo. Let us try to see that command. Print solve mod. So what are we trying to solve? X equal to, what was that? A2. A2, and here we need not even define this modulo ring. Let's try to see what this is, or even A2 is what? A2 was 2. Let us see what the output is. X equal to, what is the error here? Object has no where exactly the error is appearing. Let me just see equation. Okay, have I done something here? A2, let me just remove these things. Even, okay, this is also not probably necessary here. Let me just redefine X to be this. Yes. So because X was needed to be a usual variable here. So solve modulo X equal to 2 is something, is this correct? 5 X congruent to 2 modulo 5. Yeah, that's probably correct. That's only one solution we are getting, right? Okay, that's 2. Now let me just try to take X congruent to 8. Now probably one more. Will it work? I don't know. It should definitely work because X congruent we are trying with X congruent to 13. Must be the same answer, of course. Otherwise we cannot get. Now maybe 2 star X, 2 is going to work. 2 star X equal to this. All these things are working. Updating the Google document. Done. Now, what about Chinese remainder theorem? Let us try one problem in Chinese remainder theorem now. So, what we should take? Let me just take one problem. X congruent to 2 mod. So, relatively prime we need 2 mod 4, 4, 5, 6. No, 3, 4, 5. Let us take 3, x congruent to 3 mod 4, x congruent to 3 mod 5. Or 4 mod 5, whatever. Now the problem here is that the solve modulo is actually looking for one argument that that moduli has to be very common. Moduli has to be the common moduli, because x congruent to 8, x congruent to 13, both these things you are looking for modulo 5. But here the problem is that we are using different moduli. In this case, the solve modulo that cannot actually be applied, because in solve modulo the first argument is nothing but it's the list of equations that we want to solve, and the second one is the modulo. Therefore, this will work only in one particular integer ring. So this is not going to work everywhere. So what we can probably do is we can try to see if there is a solution for this solve modulo. Chinese remainder theorem guarantees that there is a solution, and that solution is actually unique in m1 into m2 into etc. mn. But even then, we cannot say that that solution is going to be, if we solve the equation in m1 into m2 into etc. mn, we are not going to get a1, a2, a3, etc. up to an everything. We will be getting only one number, right? But how do we know that that number is going to fit that m1, that number is going to fit that m2, that number is going to fit that mn, all these moduli? That's the question we have. Let us try to see if that's actually a correct solution or not. Okay, let us try to just solve it in terms of m1 into m2 into mn, and let us see if that is equal to, if that satisfies 2 mod 3, 3 mod 4 and 4 mod 5. That's one possibility. So trying to solve. All these simultaneously. X congruent to, so x congruent to which one? So x congruent to 2, let us take. So if you take x congruent to 2, what will happen is you will be getting what do you call it, 2 itself, because your moduli is more than that, so you will be getting, so that's not going to make much sense. So instead of that, there is another command available in SageMath, which is known as the CRT command itself. Okay, Chinese remainder theorem, for solving problems related to that, there is already a built-in CRT function available in SageMath. So CRT function just asks for the residues and moduli. First we need to specify the residues, then we need to specify the moduli. That's it. So let's try to see that. CRT, let's give the residues first, 2, 3, 4, and now give the moduli, 3, 4, 5. The solution is 59. So how do we verify this? Solution we got to be 59. How do we verify this? Take 59 mod 3. Okay, take 59 mod 3. So let us take the solution to be this variable. Now take solution is this. So what are the things that we have to check? Solution modulo 3, solution modulo 4, solution modulo 5. So 59, 4 itself I have it. 2, 3, 4. So this solution is the solution for the CRT part. Updating the Google document. Done. Okay, now as I told previously, the prime number raise that problem. So if you do not remember that prime number raise problem, let me just explain it shortly. So the prime number raise problem was that previously was that. So if suppose that we know that the primes are all odd after 2. 2 is the only even prime, and after that all the primes are even, and therefore the primes can be categorized into 2 sets. One is the what do you call 4n plus 1 primes, and other is the 4n plus 3 primes. Okay, there are 2 types of primes falling into for either modulo 4 equal to 1 primes and modulo 4 equal to 3 primes. So the question that we discussed in the last session, the problem was that, so which type of primes are more? So there has been a proof that number of 4n plus primes are infinite. There has been another proof also that 4n plus 3 primes are infinite. I think one of them is provided by directly, and the other result is quite easy, it seems to be, and the other one takes a little bit time to solve. So both these results imply that both these primes are infinite. The set of both these primes are there in infinite. Therefore, now the question is to actually determine. So whenever there is something called the number is infinite, so we try to estimate it at some particular finite point of time in that on that number line. It means that suppose that we consider primes up to 100, then which of these primes are going to be more? 4n plus 1 primes are more, or 4n plus 3 primes are more? Now suppose that we are considering up to 1000. So which of these primes are more, 4n plus 1 or 4n plus 3? So this essentially means that we are trying to see at any given point of time, can we certainly say that one particular prime is going to be always more after that particular time, which means that after 100, can we definitely say that 4n plus 1 primes, number of 4n plus 1 primes after any number after 100 is going to be more than that of 4n plus 3 primes? That's the problem. Okay, let me just try to see. So this actually gives you an interesting problem in number theory, and as I told, this actually gives us an insight into sometimes this software is actually very inferior to human mind. Okay, so we are trying to learn something called mathematics software, but mathematics software is not actually a replacement of human mind. Human mind is much more powerful, is what I think, because we can intelligently think, we can intelligently intelligently branch the problem into several pieces, and we can try to probably efficiently find out solution, not probably much faster, but most probably much efficiently, and sometimes the software will be completely unable to find solution which a human mind will be able to. Okay, that's what we are trying to see. So the problem is prime trace. Which primes are more, 4n plus 1 or 4n plus 3 at a given point on the number line? So to test this, let us try to see the number of primes up to specific numbers. But before that, we are going to do another thing. So remember that 4n plus 1 prime means that we are supposed to take primes from the set of all primes, and after that we are supposed to take modulo 4. Modulo 4, it will be either 1 or it will be 3. But for understanding the problem in a better way, if you take the modulo to be either 1 or minus 1, because remember that 3 is nothing but modulo 4, it's going to be equal to minus 1. So if you take 1 and minus 1, it will be really easy for us to compare these two things. Because if we add up these two things, if we are getting, suppose that up to 100 we take 1s and minus 1, and suppose that we add and suppose that we get it to be equal to 0, that means that 4n plus 1 and 4n plus 3 are exactly the same. Suppose that we get a positive number, it means that 4n plus 1 is more. Suppose that we get a negative number, it means that 4n plus 3 is more. Okay, that's logic that we are going to apply. Therefore, we are trying to convert 4n plus 1 primes and 4n plus 3 primes into 1 and minus 1 modulo 3. That's what we are trying to do. Okay, so let us start. P equal to primes. Let's define. Now let's try to take primes, and each and every step we will try to add also. So prime moduli. In the last session we discussed about a function called count, but we haven't tried that. So prime mod 4 that we are going to trying to see, prime, that is just a name, prime mod 4 equal to, let us take the modulus of the primes, or let us take initially not this command but primes in range instead of that, because this one will be giving all the 100 primes or whatever number we are asking for. Primes, prime range 1, 2 or 2, 2 or 3, 2 even. 3 to 100. Let's see what this is. Okay, we are getting from 3 up to 97. That's correct. Now, prime mod 4. We are going to take all the primes mod 4. So if we take modulo, after that we'll try to convert into minus 1. P mod 4, 4, P in P. Let's print it with this. 3, 1, 3, 1, etc. This is what we are getting, 3, 1, 3, 1, 3, 1, etc. Now, let's try to convert this into negatives. Okay, how to get the negative number is what I am thinking. Otherwise, we may have to just convert everything instead of replace. Okay, let us do it in the hard way. So just let us take pi mod 4 equal to what should we do? So the question is how to convert this into negative.
Sir, I'm not getting your question. Can you?
What I want is, so I will explain that. So my plan is the following. Suppose that we have here the numbers are appearing as 3, 1, 3, 1, 3, 3, etc. Okay,
Right.
you agree to that? So suppose that we replace this 3 with minus 1, negative modulus. So negative remainder, not modulus, negative remainder.
Okay.
If we replace it with a negative remainder, if we take the sum of all these things, we will be getting either 1 or minus 1 or sorry, either a positive number or a negative number or 0.
Okay. So the number less than that is less than 4. Then it will come the minus. Or the other will be the more than 4, so it will be positive.
No. The remainder usually we take it as we can take the remainders to be remainder by the division algorithm. It's always going to be positive. But in the case of congruence rings, sometimes what we do is for the sake of handling them easily, we take it to be negative also. For example, instead of taking the power of 3, it's easy to take the power of minus 1.
Okay.
So if we if we allow the remainders to be negative, so in that case what we will do is instead of taking the remainders to be 0, 1, 2, 3, we take the remainders to be minus 2, minus 1, 0, 1, something like that.
Okay.
So minus 1 will be a remainder. Minus 1 will correspond to this 3.
Hmm.
Now I essentially want...
So in this case we'll get only, we want to get minus 1 and 1.
Yes, minus 1 and 1 I want, but I am getting only 3. That's what I am checking.
Okay.
I want this to be negative. The negative that I want, so that I can easily handle that the addition and multiplication, everything will be easier. Let me just check. If there is no other way, we may have to simply replace.
Negative remainders are also allowed.
Sorry?
The positive remainder means we want to take positive remainders or negative remainders.
I want 1 to be a remainder, and instead of 3, I want a negative remainder, minus 1. So if that's not possible, we may have to replace. That's what I'm thinking. Replace the entire 3's with so we can replace, of course, in a for loop or a while loop, but that is not actually a best thing to do, because or otherwise you may have to define some if else kind of thing. P percentage for
Yes.
but that also
If that is more than equals to 3, then it is minus 1.
yeah, P percentage for P in if, maybe we can do this. P percentage 4 equal to 3 or minus 1, but and we may not be able to do is what I think, and I don't think that will work. Okay, let us just try.
Right. Well, let's take minus 1.
But going through there is 2 times is going to work, that's the question. And P percentage 4 if this is just 1. This is what I essentially want. but will this work? -1, 4, P in P, if P percentage 4 is 3. Okay, let us just try to remove this and see if this is at least working. Okay, this is working. Otherwise, we may have to just club them together. 3 mod 4, but that is not very efficient. Okay, still, if there is no other way.
So -5, -5, -9.
-5, where is that?
No. Means they will give remainders as -1.
Yes, because we have already taken P percentage 4 is equal to 3. We have not taken the entire thing.
Oh.
Okay, this is of course going to be possible, equal to 3, sorry, 1. Suppose this, or otherwise we can just take a plus. But of course they are not going to come in the order, but that doesn't matter. We are not interested in that order anyway. Prime mod 4. Yes, here you are getting 1s and -1s. Okay, this I have added, right? So whenever P percentage 4 is 3, I took -1. Whenever P percentage 4 is 1, I took 1. That's what I did. So is that fine? So I hope that you understood what exactly I did. So whenever a 3 mod prime is appearing, I took -1. Whenever a 1 mod prime is appearing, I just took 1. I clubbed both these lists. Okay, I clubbed both these lists. Now I am going to run a loop for n in range. Yes, is there any question? Someone raised the hand, it seems. I don't know. No, okay. So what I have done is I have just taken this. Okay, let me just remove all these things. Now we are going to do these things in a loop for this in range 3 to say n. Sorry, not n. 100 we will take initially. After that we will change. So prime range n 3 to n. So 3 to 3, after the initially it will be 3 and 3. So 3 will be definitely there. I do not want this. I want sum of all these things. Let's see what happens when we take primes in the range up to n. So what is the meaning of this? What we can conclude from this? So if we take the first prime, so primes up to some, why is it like this? So why we are getting this to be equal to 0, prime mod 4, why we are getting it to be equal to 0, up to 3. The first prime at least should have been printed, right? First prime at least we should get 3 at least we should have considered. Why we are getting it like this? Prime range 3, 3. Are we not getting anything because of this? Okay, first time I think we are not getting this. So maybe we should take it from n in range 4 to, let us take. I think that's better. So this essentially means that when we are taking primes up to 4 minus 1, primes up to 4, we have minus 1 is minus 1 appears because 3 is the only prime and 3 we have converted into minus 1. So when we take primes up to 5, we are still getting minus 5, but minus 1, but that's not correct, right? How is that correct? So 3, after that up to 5, okay, up to 5 means that 5 is not probably included, right? 5 is not included, okay, so this is an open interval kind of thing. Prime range 3n is an open interval kind of thing where primes from 3 up to n and n is not included. Therefore, primes below is the correct word. Primes below 4, minus 1. Primes below 5, minus 1. Primes below 6, 0. Because 3 is, and even 3 is a prime, 4n plus 3, and 5 is a prime, 4n plus 1. Therefore, at 6 what happens is that there are 2 primes, the 3 prime and 5 prime. Both these primes are having 1 and minus 1, therefore sum is 0. Okay, so maybe instead of even this, let us just try to so okay, what happens is after at 6 what happens is that these 2 primes are exactly the same number of primes appear, which are 1 mod 3, 1 mod 4 and 3 mod 4, same number of primes at 6, same number of primes at 7, because at 7, below 7 the same number of primes as that of 6. Below 8 what happens is the sum is minus 1. Sum is minus 1 means that plus 1s and minus 1s cancel and 1 minus 1 is 1 minus 1 prime is remaining. Minus 1 prime corresponds to the 4n plus 3 prime. Up to 9 exactly the same, 10 the same, 11 the same, 12 the same. So 12 not the same, 12 it has become minus 2. Minus 2 means that there are more 4n plus 3 primes than 4n plus 1 up to 11. Minus 2. Minus 2 means that up to 13, in fact below 13 there are more 4n plus 3 primes than 4n plus 1 prime. So 13 is actually a 4n plus 1 prime. Therefore, this minus 2 plus 1 added and therefore it became minus 1. So even here minus 1, 4n plus 3 primes are more. 4n plus 3 primes are more. 4n plus 3 more. 4n plus 3 more. Up to 17 the number of primes are exactly the same. Okay, 4n plus 1 and 4n plus 3 primes are exactly the same. That's why they cancelled each other. Minus 1s and plus 1s cancelled each other. Now again 4n plus 3 is leading. 4n plus 3, 4n plus 3, 4n plus 3, 4n plus 3. Again cancellation. But you can see one thing. You can see one interesting thing that never this value becomes positive. Never this sum becomes positive. But sometimes this becomes more and more negative. So what is the meaning of this problem? How do we interpret this result? Any guess?
So it is most of the form is like 4n plus 3.
Most of the primes are like 4n plus 3. Exactly, that's correct. Okay, to understand this problem in more, see, we have observed each and every prime and we have taken this sum. So to understand this problem, what we can do is that we can actually plot a graph. We can plot a graph of this number. Since we have a discrete set of numbers, we can try to do the list plotting. Okay, let us try to plot the list plotting. So what is the list? The sum is our list. So prime sum, we will call that list to be. Prime sum is an empty list, and after that we will keep on appending values. what we will append? This we will append. This sum we will append. So we'll get minus 1, 0, 0, minus 1, etc. Now let us see P t equal to, just giving that PLT name, or prime plot. Let us give that name. List plot. What to plot? Prime sum. Let us suppress this prints to see it easily. Okay, let me just update. We are going to discuss this again. Let me just update the Google document. Okay, let's now increase the number. Okay, I have updated the Google document. Let's increase this number from 4 to 300, say. So now let us change it slightly to a higher number. So what do you understand from all these things? That's see, the graph is always below, or at most it's on this line, on the x line, x-axis. It's not going up. It's never above the x-axis. Increasing it further, taking more time. So The surprising thing is that so what now actually feel is that the primes are actually it has a bias to this minus 3 primes, right? 3 primes. So primes are more and more biased because you can see that it actually forms a kind of curve. It becomes thick and thick, but it's actually coming more and more down. Each and every moment what happens is that when we observe from a distance, what we can see is that the primes, the total number of summation of these primes, if we take with plus 1 and minus 1, it's coming down and it's going below 15, it's going below minus 15, and it can probably go further down, but it's coming up also. It's coming up and it's trying to touch the x-axis, but it fails. It fails. Okay, in the range, in the at the x value, when x value is equal to around 6,000, when n is equal to around 6,000, it's going further down. I think it goes down to some minus 20 or something like that. But it again tries to bring its head up and reaches after 8,000 very close to this x-axis at some minus 3 or something like that. It again fails. It goes down. So we can definitely see that there is actually a bias towards this 3 primes or minus 1 primes. Okay, so the question that mathematicians discussed was that is the number of primes, is this bias is going to continue forever? That means that can we certainly say that these 3 primes, mod 3 primes, modulo 4 3 primes, they are going to be always leading or not? That was the question that that was asked by one famous mathematician called Chebyshev. Okay, Chebyshev was the first person probably that who noticed that it's going like this. That modulo 3 primes are more. Okay, and
This problem we can do separately also. Is we count the numbers which are of the form 4n plus 3 form or 4n plus 1 form.
I didn't understand your question. What we can do it separately.
Here we are giving values minus 1 and we are adding. If we do the problem separately, means we count the numbers which are of the form 4n plus 3 or 4n plus 1.
Yes, certainly we can count and compare. That's also possible. If you want to count and compare, what you have to do is if you count, what happens is that you may have to plot 2 separate graphs. Okay, in that case, if you are counting, you will be having 2 separate graphs, and from these separate graphs, it may not be easy to identify that which one is actually up and which one is actually down, because we are plotting as a list. So we have some discrete numbers only.
Yes. Yes.
But if you are adding, the good thing is that whenever you are adding, you are getting either 0 or 1, 0 or you need to just worry about if it's above the x-axis or below the x-axis. That's it. Because we are going to get a positive. If we are getting a positive number, it means that at that particular point of time, the modulo 1 primes are more. If you are getting a negative number, it simply means that the number of primes modulo 3 is more comparatively.
Yes.
So if it's 0, it essentially means that they are balancing, but that balancing is not happening as per the picture. Therefore, that's why we use the summation method. Of course, you can plot it separately, but this actually gives a better understanding of the problem. That's it. If you take minus 1 and 1, they will add, they will cancel, and we need to just look at this x-axis line. Nothing else is relevant to us. Otherwise, we need to compare each and every point. If it's otherwise, you are comparing with 2 lists. Here, you are comparing only with the x-axis. X-axis is x-axis is a straight line thing. You can easily see, but the other one it will be a little bit difficult. So we can even try that. So this is one thing. Okay, let us just copy this and paste, and see what you have, and let us try to do what you have suggested instead of this. So 2 list plots are required there. Suppose that we are taking p percentage 4 itself, and this is not required because definitely we will be having either 1 or 3, so no need to use this. So prime mode 4 is just this. Now there is no need to append the sum. We don't have to take the sum, but instead of that, so we need not prime sum. So we will prime count. So how many are there up to here that we are going to count? Count 3. So 3 we are counting. Prime 3 count. Suppose we take this. Now suppose we take the other count. So how many ones are here? Then we need to plot both these things, not summing, there is no summation. Okay, we need to append actually, sorry. So we need to define two lists, prime 3 counting list, prime 1 counting list. To this we will append this count. So this count, so we have two lists. Now we will plot. Let's plot prime sum, not sum. Prime 1 count. Let us see what is the output of this. Prime 3 count, maybe in different colors. Blue itself is 1. Black. Oh, we have taken a huge number. Okay. So you can say that black is more, right? But it's not very obvious. It's not very obvious, not very clear.
Yes, sir. Yes, sir.
That's why I told. That if you are summing, we have to only look at one particular number, one number. So it's not very, otherwise it's not very easy to identify. How does this look?
Thanks.
So if you go for a huge number, one more zero I added, but even that's not going to be sufficient. Running. Hello, am I audible?
Yes, sir.
What happened is, because I used some huge number, what happened is my system got hung. So I had to restart. So that's the issue.
Sorry.
Yeah, that's the issue. If you are using a huge number in a system which is not very powerful, the finding primes is a memory taking task. Not only that, we were trying to append all these things to a list, and this was not at all an efficient operation that we were doing, but still that is the only way to see the problem in action. So anyway, let me just restore everything else. So let me just change it to a small number, because otherwise it will again create some trouble. Which number I used? Comparatively large one. Maybe a small one I'll stick to. So yeah, what I
So
told
your
is, yeah.
screen is not screen is not visible.
Okay, sorry, I didn't share. Is this okay now?
Yes.
So okay, so I reduced it to, I changed it to a number 1000. Now if I change it to just 100, so you can see that it's appearing as, see, something like this. So if the black dots correspond, if we see that the black dots correspond to prime 3, the black dots are more or less above the blue dots, and in some way, at some places this blue and black are almost on the same line, almost at the same level. If you increase it to 1000, what happens is that you can see that most of the times this blue one is below this black line, and at some places this blue one and black one coincides. In the finite range, the very small range that we are observing, we can say that this blue line is never going above this black line, at least. So I think we safely tried up to 10,000. There were no issues. 10,000, up to that it's fine. So you can see that these lines are going after some time more or less close to each other, but we don't know that's actually correct or not, because we are seeing it for some large number. Therefore it's quite possible that in between there are some gaps. At least here you can see that there is a wide gap. So from this finite data, very small data we are observing, we can say that the prime 3 primes are more. The question that Chebyshev asked was, is this going to be the same always or not? Is it going to be the same case always or not? That means prime 3 modulo 4 primes are always going to be more or equal compared to prime modulo 1, modulo 4, 1 modulo 4 primes. That's the question Chebyshev asked, and it was actually hardy, and it was actually found that at a huge number, what happens is these two primes are at a huge number, at a huge n, prime 1 modulo 4 primes are actually overtaking these 3 modulo primes. So the overtaking actually happens. I'll share one link with you. This link is going to be somewhat useful. So this actually tells you some details about Chebyshev bias, which is essentially what we are discussing about the prime race. So 1 mod 4 primes are more, or 3 mod 4 primes are more, and it was observed that at a huge number 1 mod primes are actually becoming more. And finally it was Hardy who answered that not only that at one particular point this 1 mod primes are becoming more compared to this 3 mod primes. What happens actually is that this 1 mod primes are actually becoming much more comparatively. Okay, 1 mod primes are actually becoming not much more. 1 mod primes are overtaking this 3 mod primes every now and then, frequently. That's what it happens. Frequently in the sense that again it happens that 1 mod primes are overtaking 3 mod primes, but most of the times 3 mod primes are remaining on the top. Again it happens that 1 mod primes are overtaking. Again it happens that 1 mod primes are overtaking. It happens frequently. It happens infinitely many times, is what Hardy proved mathematically. See that? We have tried to do this, we have tried to see this using a software, and we were not that successful. Even using my machine is not that it's bad, it seems. It's comparatively a moderate machine. Even that machine, I could not verify that using some computer software. But a mathematician called Hardy, when there were no computer at all, he could verify mathematically that this crisscrossing of this modulo 3 primes line and the modulo 1 primes happens infinitely often. But still, it's an open question that the percentage by which the modulo 3 primes are overtaking modulo 1 primes, the number of times, the percentage of time, the percentage of time at which this modulo 3 primes are above this modulo 1 primes is more or not, that's yet to be proved. That's an open question in number theory.
So, what Hardy proved, I cannot understand. Means he proved that number of times of the font 4n plus 3 is more than 4n plus 1.
What Hardy proved is there exists infinitely many n's in such a way that at that particular n, 4n plus 3 primes are becoming less. Total number of 4n plus 3 primes are becoming less compared to 4n plus 3 primes.
Okay, so 4n plus 1 is less than 4n plus
No, infinitely often. That's what I'm saying.
Infinitely often.
Yeah, immediately what happens is that this 4n plus 3 becomes again more. After some time, after a huge number, again this 4n plus 1 becomes more. Again after 4n plus 3.
From your graph, it is also clear.
Which is very clear. Is it clear that 4n plus 1 is becoming more?
Yes.
No. How can we say that?
Earlier graph, from your earlier graph.
No.
This one? No, this one is not very. This one actually gives a very clear picture that 4n plus 3 is much more.
Yes.
No, what I'm saying is 4n plus 1 is also becoming, at one point 4n plus 1 is overtaking this 4n plus 3.
But till now, no one can find out that particular range where it is overtaking that 4n plus 3.
Yes, there are a few numbers they have already found, but infinite number of numbers we cannot definitely find.
Okay.
So the n at which, okay, I am copying and pasting the content from, okay, I cannot copy and paste. So the n where number of 4n plus 1 primes are becoming more than 4n plus 3 primes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That n has 11 digits.
Okay, 11.
That's a huge number. After that again it happens. And in fact what happens is, after that 11 digit number, more or less close to that 11 digit number, 3 or 4 times this overtaking happens. 4n plus 1 becomes more. Again what happens is 4n plus 3 becomes again more. So most of the times, according to the observation, 4n plus 3 are more. But that is not actually a guarantee that 4n plus 3 always remain more compared to 4n plus 1. That's not a guarantee. Hardy proved that it's the other way, that it overtakes. Once in a while the overtaking happens. And again 4n plus 3 definitely becomes more. But it is not the case that 4n plus 3 is always leading. That's not the case. There is no permanent winner. That's what I'm saying.
Okay.
That's a very interesting problem in number theory, that such a kind of thing. Chebyshev, a very old, a mathematician from an old age, he observed this thing that 4n plus 3 is leading. After some time, some people empirically or using some other technique probably, they found that this crossing actually happens. The question after that was that is this crossing going to happen infinitely often? And Hardy answered that yes. This crisscrossing of these two lines, 4n plus 3 primes and 4n plus 1 primes, or otherwise the 4n plus that summation 1 minus 1, it actually crosses the x-axis and it goes above the x-axis infinitely often, and it goes below the x-axis also, of course, and it remains below the x-axis most of the times is what we have observed. But that also I don't think that has been theoretically proved. That most of the times in a finite, up to some finite number, of course we can see using some software, but is it going to happen infinitely often is not very clear. That most of the times, most again means that the percentage. So whatever number you are taking, can you definitely say that 90% of the time, for whatever number you take, it's going to be 4n plus 3 is going to be more compared to 4n plus 1. That's not very clear. That answer is not there. This problem is known as prime race or Chebyshev bias. So the link I have shared is the Wikipedia page, and you can definitely find it in many other places, this prime race related thing. And of course you can implement all these things in Python also. But Python, the difficulty is that you have to find out, you have to write your own function for constructing primes. In Python, I don't think that there is a built-in function for finding primes. Okay. I haven't have I copied and pasted. Okay, let me just open the worksheet. Is it open already? Yes. Let me copy and paste the second picture also I generated. But of course, I think we can optimize this so that optimize this program so that this will not hang and we can actually see that crisscrossing at least for the first time. If you try to optimize, because here we have what we have done is that our program is not that much efficient in the sense that we are locating each and every prime. So every time we are taking the primes in this range. After that, every time we are creating in the list. This is not actually necessary. And again, we are counting each and every time. But once we have counted up to some number, we need to count only after that number. So we can optimize this program to make it much more efficient so that it will not hang like this. See, here we are doing these operations repeatedly. We are finding, for example, suppose that we are finding prime from 3 to 100. So what is the need of finding prime from 3 to 100 again? We need to find primes from 3 to 1 to 100 to 200 only after that, because already we have the primes from 3 to 100, right? So in the same way, we need not count these primes from beginning up to the 100th prime. Once you counted up to 100, you need to count only from 100 onwards. The previous count is already available to you. Therefore, you can write a better code in such a way that the program becomes less memory hungry, and maybe it can compute for larger numbers. So this is not actually an efficient program or a very good program. It actually tries to demonstrate using minimum number of commands. That's it. It's not the best one, of course. You can probably try to write something better. Okay, let us go into the next problem. Oh, all the files I opened got closed while restarting. Let me just open which file I was typing. Let me just see. The file the theory. Okay, now we will go into what is the topic that we were supposed to discuss. I'm just checking. Now, So the number theory part is complete. So permutations, I think we have already seen. Combinations, finding GCD, prime counting, and the prime divisors, counting devices, modular arithmetic. What are the things left for us now? Problems in number theory, linear definite equations we have already solved. Chinese remainder theorem we have seen. Uses identity. Okay, let us go to the complex analysis part a little bit, and after that we will try to see something related to constraint optimization, calculus, maximum, glory, definite integral. Okay, so a little bit of complex analysis we'll try to see now, because we have most of the number theory, I think basic things we have seen. Now one more thing probably we can try is the implementation of the RSA algorithm. If you are interested in, we can try to even discuss that, and that RSA part also. So RSA algorithm, that's going to be interesting only provided that you are interested in a little bit of number theory. Otherwise that's not going to be very interesting. So abstract algebra, I'm just trying to see which actually can be. Okay, let us see some complex arithmetic. Yeah, please.
Actually, I don't know about this RSA, but if you provide some material for it, I may know it, and actually if you tell something about it, actually I am interested in cryptography, but I don't know much about it.
So okay, RSA cryptography, I can quickly tell you I cannot completely explain, but I can give you an overview of that thing. So RSA cryptography essentially means that we are the encryption, decryption, these two things probably it's familiar to most of us, that because we are using this computer, we are using this email kind of thing, passwords, etc., etc. Therefore our passwords, whenever we are transferring across the internet connections, in the sense that suppose that we are typing the password in our system and we are clicking the submit button. For example, in Google Chrome, suppose that you are opening a page and suppose that you are entering your password, you click on submit button. What happens is that the data now passes through the optical fiber cable or the mobile internet data tower. So whatever password we are typing, it passes through the tower, and finally it reaches the the Google Gmail server. Okay, so in between what happens is that our password is passing through some medium over which we don't have any control. Over the system in which we are typing, we have some control. So we know that from our system nobody is going to steal the passwords that we are typing. So it's very clear to us, we are confident about that. When we are transferring it across optical fiber, remember that the optical fiber is connected to a server which is controlled by our internet service provider, optical fiber cable, or the data tower or mobile tower used through which we are transferring the data. That is under the control of someone whom we cannot actually trust. We don't have any trust over him because we don't know who exactly this person is. Therefore, it's highly possible that our password can be seen. See, because suppose that we are talking over a phone, right? Suppose that we are talking over a phone to someone who is sitting at a distance. Therefore, the person who is sitting in the telephone exchange will be easily able to hear what exactly we are talking about, because the data is passing through his system. It's like this. So that is not actually happening. Why this is not happening? That our data is, even though it's passing through the server of a person whom we do not trust, this stealing of the data is not happening because there is something known as encryption happening. So the data from our system is not actually going exactly in the same way as we are typing. The browser actually encrypts the data, and the data is now shared with the Google server. So using which key the encryption is happening? Actually, the key for encryption is actually given by the Google server. The Google server actually gives the key to the Firefox for Firefox or Chrome. Gmail server is giving a key to Google Chrome. Google Chrome uses that key to lock the password in a box. So the password locked inside a box is transmitted to the ISP server. ISP means Internet Service Provider. Since the password is inside a box, the ISP service provider can see the content of that box provided that he is able to open that box. But opening the box is really difficult because the key used for closing the box and the key required for opening the box are different. Okay, these two keys are different. The key used for locking and key required for opening, they are not exactly the same. Now, who has the key to open that? The person who has sent the locking key only has the opening key. But who is that person? That is the Google server or Gmail server. Therefore, when the password reaches the Gmail server, what happens is, using the key, Gmail opens this box and sees what type of password is there. What I'm saying is actually simplification of the entire process. It is not actually happening exactly in the same way, but you can think of the RS implementation something similar to this. So,
hello, sir.
yes.
Like we can think this like there are two person A and B, and like person A wants to send a text message like M. We are denoting that message by M to V.
Okay.
And in between the A and V, there is a attacker.
Yes.
Who can steal our message. Like
Yes.
we are like chatting on WhatsApp, we can consider that case. We are chatting with some person, like some person V. And so A wants to send a message to the guy B. So like that message is like M. So with the help of a function, encryption function, like he is not directly, the person A is not directly sending the message M. With the help of a function, that is like we are stating that like a key. So with the help of that key, he is like encrypting a function in a different language. M. Directly he is not sending the M. He is typing M, but that function is encrypting in a different language so that the attacker can't understand that message, what I am texting some other guy. So with the help of that person, like F is a function and M is our message. So F of M is the message that the recipient will receive, and with the help of that inverse function, the receiver will receiver find the inverse of that function, and that will he will apply on F of M. So F of inverse, he will apply F of inverse of F of M, and he can easily find the M. But this function should be in this way that the inverse, finding the inverse of this function must be, very, very difficult. So it will like protect our conversation, but it can also be broken. So that's why the RSA will come into the picture like this. This
Okay.
is the
Okay,
preliminary basic
thank you for the explanation. So, the main issue that one tries to understand in this is that most of the people will not be encrypting this. Okay, most of the people will not be doing any encryption from their side. Whenever we are typing an email message, whenever we are typing the password, what we are typing is we are typing exactly the same password. Therefore, who is sending this encryption function? That's actually one question. Who is sending the encryption function, and who is converting this this password into something secret? Okay, these two are the things that I think many of the people may not actually understand. That's why I want to use this example that this is essentially a communication between A and B. Here A and B is actually, A is the person who is typing the message and B is the Gmail server if we are transmitting the password to Gmail. Okay, I think whatever we are talking about, both of us are talking almost the same thing. But instead of A and B, I used the person who is sending the message and the Google server, because we will not be directly sending the message to any other person. We will be sending the message to Google, and Google is actually sending the message to the other person. There is an intermediate again. So is that correct?
Yes.
Yeah. So somebody has to give the key, but who is going to give the key? Because the other person sitting on the other side, he is not going to give the key to us all the times, because we will be sending email to hundreds of people. But we cannot wait for the key to come from each and every person for encrypting that key to encrypting that message to be sent. Because in that case, the problem is that suppose that I want to send a message to a person, and then I need to get his key. Suppose that I want to send a message to another person, then again I want to get a key. Right? But we are using only one password. For each and every message, we are signing into the Google system and we are using one password. So, how do that password system is actually working? So, the encryption, decryption is actually taking place between the person and the Google server. So, the rest of the things are being taken care of by the Google server. Message transmission between A and B is not actually happening in the case of email systems. Message transmission is happening between a person to the email service provider and email service provider to the other person. Therefore, between whom this key exchange is happening, who is giving the key to lock? Google must be giving the key to lock. But to where he is sending this key, because we are not doing any locking or unlocking. Who is doing this locking and unlocking? Google must be sending the key to our browser where we are typing all these things. Okay, Google Chrome is actually locking. We are not locking. We are not doing any encryption from our side. Our side in the sense that personally I am not doing any locking because I don't know how to lock. I am not at all interested in this locking process. What I am doing is I am just typing a password. Then someone is supposed to apply that lock. So when we are going out of our home, someone will be locking our home, right? If not we, maybe our friend will be locking that room. We may not be knowing that it's being locked, but we will simply go out, assuming that someone who is responsible for locking will be locking this. In the same way, Google is sending one locking function, exactly what already Virendra sir has already told, that there is an encryption function or locking function which is really difficult to unlock. Unlike the usual locks, in the usual lock that we are using in our homes, what happens is that if we are locking that lock using one key, the same key can be used for opening also. Okay, but the problem is that now we are sending the data over now we are sending the key, lock, everything over internet. Therefore, if that person is getting the key also using which we are going to lock, then he will be able to unlock that, because the internet service provider is also seeing this lock and key. But that's not happening. That's because the key used for locking is not the same as key used for unlocking. That's what Virendra sir told, that one is function and the other function is inverse. So the inverse function in the usual case, in the usual lock and key case, whatever you use for locking, that's applying function, is the same as whatever you use for unlocking, the inverse function. But in the case of encryption, locking and unlocking is taking place using different keys. So this is possible only mathematically. Okay, so for locking and unlocking, we are using the RSA cryptography system. So RSA cryptography system actually provides two types of keys, one for locking and one for unlocking. So all these transmissions, all these transactions are happening not between we and Google, but instead of that, this is happening between browser and Google when we are sending the message. That's why we are not at all noticing any of these things. All these things are actually happening, but we don't notice. Right? Okay, that's more or less the story behind all these things. And now probably you can find out material about why this RSA name, because that's after three computer scientists or three mathematicians or three logicians, Ronald Shamir and Ronald Rivers, Shamir and I think Adleman. I think these are the three names. Now, if you want to implement, the thing is that how number theory is coming into the picture is that RSA is actually using the power of prime number multiplication, prime number modulo for creating key and locking key and unlocking key. Okay, let me just try to explain that shortly. I am not going into why these things are actually working. I can just tell you that how these things are working, but why these things are working, we need to understand the theory a little bit more deeply. For that, so RSA implementation, we will try to see how to implement RSA through the SageMath using some small primes, not large prime, because large prime is not within the reach of this computer where I am working. And not only that, in the RSA cryptography these days, primes of length, I think some 256 or something like that bits are being used for locking. That we cannot definitely create in ordinary systems. So that can be created only in some supercomputers. So the RSA implementation, I will just give you the steps first of all. Once you are given the steps, it's very easy to actually create it using SageMath. There is no difficulty at all. So the first step, I'll just explain the steps. Choose two primes, P, Q. So we need two primes, and we will take small primes so that we can easily understand the process. N equal to PQ, take. So this is the first step. So this is very easy for us. We know in many primes we know. Now we are going to take an integer E. This is the simplest way we can probably explain. An integer E must be in such a way that the GCD E and phi of n is the Euler torsion function. This must be 1. This is the second step. And why we are doing all these things, I already told that I'm not trying to explain that part, but how this is going to be implemented, that only we will see in Sage. These things are, let us take these steps to be correct for granted. Now what we are now trying to do is we compute a value. Now we are going to compute a value in the sense that solve for some D such that DE, the product we have found, congruent to 1 mod phi of n. So what are the inputs that we require up to here? So what are the inputs we have taken up to here? So we have chosen only two primes, P and Q, because n is actually a product of P and Q. Once given P and Q, we can definitely find n. Now the next input that we want is take an integer E so that E and phi of n are latently prime. Okay, so we have chosen P, we have chosen Q, now we have chosen E, which is latently prime to phi of n. After that, we are trying to solve for D congruent to 1 mod phi n. So D congruent to 1 mod phi n, E is already chosen, therefore we need to find only one, we need to take only one more input, which is D. Okay, so now the keys are ready for us. I'll tell you what are the keys. There are two keys. Public key, which is the pair N, E. Public key is the pair N, E, and private key is something known as P, Q, D. So what are the purposes of this public key and private key? Suppose that one of you wants to send a message to me, and suppose that so it's actually difficult that if you are asking me to give the key, I have to transfer the key to you, then you will lock, then I have to unlock using my own key. That's a little bit of kind of a difficult thing. So there is a key called public key. So this key I will announce everywhere that anyone can lock using this key. No problem. N and D I will announce publicly. Okay, I will announce it in the internet. I will announce it everywhere. Anyone can lock a message using this key NE. But for unlocking the message, even if you have logged using NE, I will explain that how to lock that. For unlocking the message, this NE is not enough. We need PQD. Then you may be thinking that once you know N, E, we will be able to find PQ and D, right? Once you know NE, we will be able to find out this PQ and D, because N is nothing but it's a product of PQ. That process is known to everyone. The process that N is equal to PQ is known to everyone. So whenever I am announcing this N to be this number, everyone realizes that it's a product of two primes P and Q. But now, for unlocking what I need P, Q, D. But how do I find this P, Q and D? I need to find P and Q. How do I find P? For finding P, I need to factorize this N. Because it's a product of two primes. But factorizing a number is actually a very, very difficult problem. It's almost impossible if you are using a huge prime P and a huge prime Q. Because after multiplication, it will simply look like a number, and for factorization, what you need? So if you are using both the primes to be very large, So if you are using one of the primes to be very small, by random trial and error, you will be able to find the one factor p. Suppose that you are using the prime 2. If you are using the prime 2 in PQ, it's easy to verify because the number will be even. Suppose that you are using the prime 3. If you are using prime 3 as p, then it is again easy to verify, because if you add the digits in n, you will be getting the sum of the digits to be a multiple of 3. In that case, 3 is a factor. So if you are using 5, then the last digit of that PQ is going to be either 0 or 5. So in that case, it's again going to be easy to determine. So if you are using a huge primes P and Q, it's very difficult to factorize n into PQ. You will be knowing n, but it will be difficult to factorize PQ. So the very basic difficulty, the inverse thing, the multiplication of primes is easy, but factorization is really difficult. It's possible, but it's really difficult. That's the essential idea. That's the most important idea behind RSA. Multiplication of primes is easy, but factorization is terribly difficult, because for multiplying, computer can do it quickly, but factorization, it will take a long time. Factorization is a terrible process. Okay, is that the concept clear to all of you? I hope that that's more or less clear. That what exactly? Yeah. The function that we are trying to create, the function that we are creating is that the basic idea behind RSA is that, basic philosophy of RSA is that multiplication of two primes is really easy compared to factorizing a number into two primes. You will not be able to do that if you are using two huge primes and given a finite time. It's really difficult. Of course, it's not impossible. By trial and error, you can definitely factorize a number into two primes, but most of the data that we are transmitting needs to be unlocked within a finite time. For example, suppose that you want to unlock within, suppose that you want to see what exactly the message is within the next 1 week, and suppose that the factorization takes 1 year. What purpose it will serve? And the encryption that we are using is not actually breakable in 1 year. So strongest encryptions will take several years to be broken. But after those several years, there is no point in actually breaking, because a secret that has a secret actually is worthy only for a finite number of years. A finite number of years in the sense that after the lifetime of a human being, what type of secrets, what type of seriousness the secrecy that he is holding will have. So the passwords, the encryption, the decryption that we are using will be really difficult to break, and most of the encryption, the keys that we are using these days for practical purposes will take the lifetime of the universe for breaking by trial and error. Okay, that much powerful it is. And that's the theory that we know. We don't know whether someone has actually found out a solution for this RSA breaking of these keys, but no one has publicly announced that there actually exists a method for unlocking this using any method other than brute force attack. Brute force attack in the sense that trial and error method. Okay, so the next step. So we have discussed 3 steps. Now the implementation is quite easy, as I told. The third step is now for any non-zero integer m less than n. Remember that n is too huge. Any non-zero integer m less than n. So m less than n. Remember that n is very large. Therefore, whatever number we are going to choose, remember that it has to be less than n. Now encryption. Encrypt m. So we are encrypting m actually using C equal to m to the power e mod n. Okay, so what we will be actually sending? We will be sending this C. That's it. This is the message that we are sending. Send C to anyone or to the person having the key P, Q, D. Now, how to decrypt this? We will try to see if these things are actually working or not. Decrypt m equal to C to the power D mod n. That's it. So for decryption, what are the things required? D is required. C is of course required. C can be seen by anyone. C can be seen by anyone. But C is not M. C is nothing but M to the power E O mod N. But how do I know N? How do I know N? This N is publicly announced. E is publicly announced. These two things are public. M is known only to me. So I am taking M to the power E. Okay, I am taking M to the power E. But if I take M to the power E, why can't I take M to the power 1 by E so that I can retrieve this? If I take just M to the power E, I have already announced this N and E publicly. So if I say that this is M to the power E, definitely one will be able to retrieve this M by taking M to the power 1 by E. But now M to the power E mod N I am choosing. So I am taking modulo also. Okay, so why we are taking the modulo? So suppose that I have a number. Suppose that I have a number 45 with me. Okay, suppose that I have a number 45 with me. I want to know that, so this 45, suppose that I'm taking, this 45 actually corresponds to, the 45 actually, so from today 12 o'clock in the morning, I am counting the number of hours and I am finding 45, okay, for completing a process. I know that 45 hours are required for completing a process. Fine. I want to send this message 45 to someone. But I do not want anyone else to know that this 45 is actually the number. So what will I do? I am going to take modulo 24. So modulo 24, what will be? 45 will be nothing but 21. So I am sending 21. But this 21, if someone is seeing, he may not be able to identify that this 21 is actually 45 or 21 itself, or it is 66 or it is 87. What exactly is this? It's difficult to identify, right? Okay, so if I send a number, modulo number, it's not very easy to identify that what exactly this number is. But N is also known. N is also, if N is known, I can actually find out. Can I actually find out? No, that's also not very easy, because even if I know that I have taken modulo 24, so modulo 24, this 45 may correspond, this 21 may correspond to 21 itself, 21 may correspond to 45, 21 may correspond to 66. Even if I know that N, it's not very easy to identify what exactly this is. Okay, so if I take the modulo, if I take the power and if I take the modulo, it's not very easy to identify that to what number M it actually corresponds to. But a person can decrypt it provided that he knows this D and N. But knowledge of D and N is possible only if D is known. But D is known only to the person who has this public. That person has P, Q and D. Okay, let us try to implement all these things. Let us see if it works or not. So the very first thing that we have to see is that we need to convert our message into a number that is less than 1 to 100. Okay. So let us choose 2 primes first. Okay, the feedback link is here, but let us finish this problem since we have started this. I'll copy and paste this to YouTube as well. Okay, the implementation part. So Google document, I think I have already shared. Since I closed, I don't have someone else. Please share this Google document link in the chat box, because when I closed, I lost that link. Okay, now choosing 2 primes first. So how do we choose? Let us see the primes in the range. So let us choose arbitrary. 59, is it a prime? You can probably ask. Yes, that's a prime. Q equal to 61. Yes, these are two primes. So what is our n? N is equal to P Q. This is the first step. Now what is E? E we want to be relatively prime to phi of n. Okay, this E we want to create relatively prime to phi of n. Fine. So which E we can choose? So for choosing E, what we can do is we let us take phi of n and let us choose. Let us find the units in phi of n. Okay. E to be. So let us just take phi of n. Phi means Euler phi. Euler phi of n. This is 3480. So what you want is a number relatively prime to this phi of n. So which number we should choose? 3480. Okay, so in fact we can choose a prime itself below 3480, of course, so that it will be relatively prime to phi of n. So maybe if you want prime range, that's the easiest thing to do.
3481.
Anything we can choose, doesn't matter. In fact, 2 itself we can choose if you want. Sorry, what you want is 3480, right? We want that to be, okay, this is not actually the method. 3481, we want something to be less than that, right? No, that's not necessary, sorry. Take an integer E so that GCD of E and phi of n is 1. So which one you told? 3481. 3480 and 3481. So for that we can choose a prime range from 3481. GCD is 1. So what is the Sage method for finding that? 3480, assuming that 2 star 3480. So 3481 is not a prime, right? So do you know the logic behind taking 2 star 3480? Why did I take 3480 and then 2 star 3480 for taking for finding a prime? That's because of a result in number theory known as Bertrand's postulate. Okay. Which says that between every n and 2n there is a prime. Okay, that's it. Between n and 2n there is a prime always. So therefore, if I choose 3480, if I want a prime after 3480, I can safely choose 2 times 3480 and ask for prime range. So that's a safe limit. That's the simplest region where we can find primes. Of course, we can find primes much before that. So choose E to be equal to 3491, the first one. Maybe I can in fact take 3480 and the 0th element in that. .349. 0th element in this list. But the only thing I need to be careful is that this phi of n itself is not, it should not be a prime, because in that case it will be taken as, okay, so I will, to be safe enough, I will take 3480 plus 1. But what is this 3480? This number, right? This number. So this number plus 1, 2 times this number plus 1. Prime range Euler phi n plus 1, 2 times Euler phi n plus 1, one bracket is missing. Okay, so I have found E also. So what are the numbers that we have found? E we have found, phi n already we have, n we have. So what is the next thing? So we need to solve for some d such that d is equal to 1 mod phi n. This is what we need next. Okay, so we want to solve for dE is equal to 1 mod phi n. So we have already seen sol mode, right? So we have already seen sol mode. Sol mode. dE is equal to phi n. So E is already there.
Sir, why is that 3480 is showing as prime?
Sorry.
3480.
3480?
It's showing prime, right? It's prime range.
3480, is that a prime? No.
But it is showing that print of the E is the prime range.
I didn't say. What I said is Euler phi of n is 3480. That's
Okay.
this number is.
Okay.
E is 3491. That's a prime. That's not necessary. It's not necessary that we should take a prime, but this needs to be prime to this phi of n. That's it.
Okay. This is a prime too.
Okay. And this number is definitely not going to be a 2 multiple of 3481, because we are choosing from 3481 to 2 times 3481 maximum. So it's not going to be a multiple of 3481. Therefore, definitely we will be getting a prime. Definitely we will get E to be a prime, E to be relatively prime to this 3480. That's guaranteed here. Now solve what we are supposed to solve. Solve dE is equal to 1 mod phi n. So what was the solve mode that we used previously? Yeah, it's here. Let's use solve mode. Solving mode. So E star D. Let's call D to be variable. E star D, or X itself is more than enough. Okay, let us try to print, and after that we will fix. E star D equal to 1 mod phi n. What did I do here? E star D equal to 1. So what is the problem here? Solve mode is missing one modulus. Is it missing? Maybe shall I use this X itself here? What's the problem here? It was working previously here. Three, 4, 2x. Have I changed the meaning of this x somewhere? Why is this working here and not here? Oh, sorry. Here there is a wrong line appearing. Okay, sorry. Okay, 253, 2531. That's what our D is. So D should be taken as 2531. That is the first entry. So 0, 0. 2531. Okay. So this first 0 was because it was inside a list. Second 0 because it was inside the list, inside a tuple was there, and inside that there is an entry. That's why I used 2 times 0. Okay. For the first entry in that list, and inside that first entry, the first element inside that tuple. So print D. Fine. So D is now located. What is left next? So the private key is PQD. That's clear to us. DE we have already solved. D is now found. So the encryption key is now the public key is NE and private key is PQD. Okay. Print. Public key is nothing but N, E, and private key is nothing but P, Q, D. Printing. So this we will be announcing. This we will be announcing to everyone. 3599 and 3491. Now, how do we do the encryption? That's the next part. The encryption, remember that we need to convert every message into a number. That number has to be less than n. Okay. So how do we do that conversion? The conversion we are going to do using the ASCII character table. ASCII character table in the sense that suppose that we have one character, we can convert that into a corresponding number in the ASCII table. So I will just show that how to do that. So suppose that we have A, x equal to or message equal to just A. So message equal to A, or otherwise message equal to in list A. This is the message, suppose. So otherwise I can just take it to be equal to A. So if I take this to be this, then order of M this is 97. So what is this order? Return the Unicode print code point for a 1 character string. That means that it gives a number essentially. So this is basically a number. That's it. Okay, so we have to convert the message into corresponding numbers. Suppose we convert hello is the message. So how do we convert now? So if hello is the message, now we are going to convert that into a number using M equal to order of what do you call C for C in M. So C in M means that firstly C will be H, next C will be E, next C will be L, next C will be L, next C will be O. Print M. What number this is going to be? This is the message that we are trying to send. This is just 104, 101, 108, 108, 111. This is the message we have. Okay, this is the message we have. Now what do we do? Now we can just take this M to be. So I just show this and just understand what exactly this is. If we get this to be what do you call a sequence of a list of numbers, now we are going to club them. Equal to, let us convert this into a full number. list M just 1 second. I'll just try to explain what exactly I have done here. So just take another cell. Let us take another cell. Suppose that this is a Z command. Z. Suppose that I take a list consisting of numbers 1, 2, 3. Suppose that I take this to be 100. What happens is this is the result. Can you guess? Can you identify what exactly might have happened here? Any guess? Okay, let me just take this to be 10. Now,
Okay, it is reverse the.
so it in fact taken 3 to 1. What it did is 321. So the first number with 1 into 10 to the power 0, 2 into 10 to the power 1, 3 into 10 to the power 2. Okay, right? So if we use
JZ is linked
set of all integers, right? So this ZZ can be used like this also. So do this process inside ZZ. So sorry. Okay, so essentially what we do is we are converting this 3 to 1 into a single number, right? But if you use 3 to 1, what happens is that this is actually getting reversed, right? 3 to we are using 1 2 3 and we are getting it in the reverse order. We are not getting it as the in the actual sequence in which we have actually created this, right? So here what we do is, instead of using this list of M, we will try to reverse this list, and then the message will be in the correct order, reversed. Okay, because the last one into M is now reversed. So this one into 100 to the power 0, this one into 100 to the power 1, this one into 100 to the power 2, this one into 100 to the power 3, this one into 100 to the power 4. But why we are doing this? Because we need to protect all these numbers. This one into 100 to the power 1, this one into 100 to the power 2, the 100 to the power 3, 100 to the power 4, 100 to the power 5. So essentially we are in, see if you are, so what is the difference between summing these numbers and multiplying and summing? That we need to see. Okay, I am just leaving that question for today. What is the difference between taking instead of this,
binary,
yes.
it is changed to binary number.
Is it a binary number? It's not a binary number now. It's a 105020909111. It's not a binary number. So another question is, why didn't we use the concatenation instead? So 104, 101, 108, 108, 111 we would have equally used, but we didn't use that, right? See, what I'm asking is, simply we would have used this number 104, 101, not without comma, 104, 101, 108, 108, 111. But we didn't do that. Instead of that, we multiplied. We multiplied each and every one with powers of 100 and then we added. Why did we do that? I'm just leaving that for the time being. I will try to explain that part also tomorrow. If someone is finding the answer, that's fine. Otherwise, I will try to explain that tomorrow also. This is how we encrypt this message. The message is now encrypted. Okay, the message is now encrypted and the number is nothing but this. This is the number. This is the final message that we have. Now, decryption, for that what we have to do is, we have to take c to the power d mod n. So, c to the power d, what is c? This is c. So, maybe I should use this as c. This is c, and decrypted message is nothing but, remember that the original m consists of 104, 101, 108, 108, 111. So the converted number, this is not actually, sorry, that's not correct. This is m itself. So we have not done this encryption, right? We have just taken m. Encryption we need to be, okay, sorry. We have not done the encryption. Encryption, C is nothing but power mode. We have already seen this power mode command. Power mode, what we have to take? So to the power d we have to choose and modulo n. D, C we have to, no, M we have to take to the d power modulo n. C, M, D, N. So what is C? This is the decrypted message. What happened here? Power mode M, D, N. What is the message? Power mode. Oh, sorry. Power mode. Stage rings and what is happening? While n equal to power mode M, D, N. M is equal to this order C. Have I used C to be something else here? Just 1 second. Okay, I think since we have, we will not get time for completing this problem. Probably the time is already, I think, 8:25. We have lost some time in between also. What we will do is we will continue this problem tomorrow and we will finish this problem and we will see how to decrypt also. And we will try to explain this part also, that why this is being used instead of just concatenation. Okay, if you are just using the concatenation, what are the efficiency related issues, what are there, we will try to see. Anyway, I will update this Google document with this, and with that probably I will stop, and we will continue the same problem tomorrow before going into the complex analysis part. Okay, so thank you very much, and if there are any questions related to this, you can either ask today or we can continue with the same problem tomorrow, or you can ask tomorrow also. Thank you.
Yeah, excuse me, sir.
Yes, please.
Sir, click Google worksheet link.
Sorry?
Please send Google worksheet link, sir.
Okay. That I think I had already shared. I will do that once again.
But due to network issue, just left the meeting, and that's why it is not showing.
Okay, it's here.
Yeah, thank you, sir.
Okay, so we will continue this problem and we will finish this problem also tomorrow, this RSA thing, and we will try to see that how to decrypt also. Okay, thank you very much.
Thank you.